Okay, so the major thing that we're going to use matrices with are going to be our three system equations with three variables. Up to this point in math, we've typically only worked with two variables. We've worked with an x and a y. Now we're going to add the z element in and the z variable in, and it's going to change things up a little bit. It's just going to make it a little bit more complicated to solve. We solved using substitution and we solved using elimination using three variables. And it's kind of a combination of both of those with three systems, three system equations with three variables. But basically all that means is we've got our three equations and they have three variables of some sort. Now you'll notice not all of the equations have all three variables in them. Like the bottom one, it does not have a y in there. That's okay because the system still has three variables. So it doesn't necessarily have to be every single equation that has the three variables. And I'm going to introduce a couple terms that we're going to use in the next slide. So looking at them right now, just bear with me. But an elementary row operation. And they're exactly what they sound like. They're elementary because the math behind them is pretty basic, pretty simple. They're either a scalar multiplication and a combination of rows, or they're switching out rows, or it's just a scalar multiplication of a row. And we use that to manipulate our rows to find what is called our identity matrix, or our row echelon form. And when we talk about our row echelon form, we're going to be talking about a 3 by 3 matrix. And remember, a 3 by 3 matrix is going to be something that looks like this. That looks 1 number, 2 number, 3 number, 4 number, 5 number, 6, 7, 8, 9. Now the only difference with our row echelon form, obviously we're going to have our x column, our y column, and our z column. And then in our row echelon form we also have what we call our solution column, and I'm just going to call that my equals column, because this is what each of these rows is going to be equal to. And we'll see how to set that up in the next slide as well. But a matrix is said to be in row echelon form if all rows consisting entirely of zeros are at the bottom. Each row, the first non-zero entry from the left is a 1, and it's called the leading zero, and the leading 1 in each row is to the right of all leading 1s in the row above it. So essentially what it's going to give us is, and now these other numbers are all arbitrary, but what I want you to focus on and what I want you to realize would be the location of the zeros and the 1s. Okay, so this is row echelon form. It's going to be any time when I have my diagonal here of 1s and everything to the left of it is zeros. Anything to the right, I really don't care what it is. So in its most basic form, our row echelon form is just going to be some sort of number, some sort of number, some sort of number. My diagonals have got to be my 1s. I could throw in my zeros, and then to the right of the 1s, don't care what they are, they can be any number under the sun. And what that's going to allow us to do is solve for our lowest variable, which is going to be our z, and then we're going to substitute backwards to find what our x and our y are going to be. So let's look at an example of this, and let's look through it one step at a time.